Lab 8 has been the most difficult of all the labs that I've had to grade, believe it or not. I'm not exactly sure why. It's just, I feel like I'm having to slog through it. One of the things that I wanted to point out to all of you, some of you have done this and done it beautifully, others have not. So I just want to share with you. You had a question in that, toward the end of that lab, that asked you to predict what would happen to the results if you made a particular error. So one of the errors was not doing the second heating. The second error was making a mistake in measuring mass, or making a mistake in the math, in using the math, using the mass. Several of you gave very vague, generalized answers. It would skew the results. It would give you the wrong amount. We know that. We know that these are errors, and we know that errors lead to incorrect calculations, incorrect conclusions. What we want for you to do is to look at the errors and try to understand how that error would affect your final results. Skewing it is not specific enough. Does it skew it high? Does it skew it low? Does it result in a calculation that's too high? Does it result in a calculation that's too low? We're trying to get you to critically think, to think about how your answers can be in error and where those errors might come from. It's very important when you compare your results to textbook measurements to understand why your answer might be too low. What kind of an error might you have made to give you a result that was too low? What kind of an error could you have made that might result in your answer being too high? That's the nature of chemistry. That's the nature of trying to understand where errors come from in your calculation and why you might want to repeat your calculation multiple times to get an average, to try to figure out where the errors are. So you need to be more specific in those answers. You're not going to get credit by telling me it would skew your results, or it would mess up everything, or some sort of a generic answer like that. You need to be more specific in your answers. So that's basically that. Now, I hope to have that lab finished today, and I will spend some time tomorrow working on lab 9. Lab 10 is the one that you're working on now, and so hopefully by the end of tomorrow I will have caught up. I'm hoping that lab 9 is just annoying to grade as lab 10 was. It's been kind of an annoyance. Okay, so we will be doing the quiz later. In the meantime, I would like to just do I'm going to do a few problems with you today, and we're going to finish up the chapter. So I think this is the one that I want. Yes. Okay, so how would we use stoichiometry? There's a variety of ways, but it's a quantitative analysis. You're talking about quantitative, meaning that it is numerical. It's a measurement. It's to determine the concentration of a substance, or you can use it to calculate the amount of product that you can collect. And there are a couple of things that are required. First of all, the reaction stoichiometry must be known. You need to know the relationship between the reactants and the products in order to be able to do this kind of a calculation. So there are a couple of different types. The first is a titration. In this, you're going to calculate the concentration of a solution. It can be determined by a reaction with a solution whose concentration is known, or through the mass of a solid, where you know what the molar mass is. And we'll look at a couple of those. The second is, by the way, another name for a titration would be a volumetric analysis, because you're measuring volumes. You're adding liquids together, or adding a liquid to a solid, and you're calculating it accordingly. The second is a gravimetric analysis. This is what would happen if you collect a solid mass. If you have an insoluble precipitate and you collect that solid mass, and gravimetric, as you could imagine, means you're going to weigh it. So you're going to weigh the product, and from that you can calculate what the concentration of that species was in your original solution. And finally, combustion analysis. We have talked about these before. You can calculate the empirical formula of a hydrocarbon determined by combusting that, and the products are always carbon dioxide and water. So let's look at, there are two different types of titrations. One is when you have the unknown is in your Erlenmeyer flask. So I have an Erlenmeyer flask here that has an analyte. Analyte means that is the substance you are analyzing. It contains an unknown, or the concentration is unknown of that species that's in the Erlenmeyer, and you want to determine what its concentration is. The solution in the burette is known as your titrant. The titrant is a solution that has a known concentration, and you add that titrant to the analyte. So you can measure the moles of the titrant in the burette by calculating the volume added. It's a known concentration. Volume times molarity gives you a number of moles. Knowing the stoichiometry between these two is important, because then from the moles of titrant that are added, you can calculate the number of moles in the analyte in the Erlenmeyer. And from that, if that analyte was a solution of unknown concentration, you can get molarity of the analyte from the moles and the volume. If it was a mass, in general, if you have a solid analyte, you will dissolve it in water, but you measure it by mass first. So you measure the mass of that analyte and then dissolve it in water. And then you can compare the moles of the analyte to the original mass that you measured. Now, the end point of any titration is when you've added exactly enough of your titrant to completely react with the number of moles in your analyte. Sometimes the reaction is not visible. You can't see where the amount of analyte is, you can't see where the end point is, or the equivalence point. Equivalence point means that you have added an equivalent amount of titrant or moles of titrant to the analyte present. If that equivalence point is not obvious, then you would add an indicator, and that happens in acid-base reactions, because the net reaction in an acid-base reaction is H plus OH minus producing water, and that's all colorless, clear and colorless. So you can add an indicator that would tell you when that endpoint occurs, or that equivalence point earns. That's called the endpoint. When the indicator changes color, that's called the endpoint. And you would choose an indicator that has an endpoint that matches your equivalence point as closely as possible. We'll talk more about that when we talk about acids and bases again in second semester. The second type of titration is a standardization, and this is what would happen when you have a solution that you want to use as a titrant, but you have to verify its concentration. So that's called a standardization. You're standardizing your titrant. And in this case, the burette contains the solution of unknown molarity. And you're going to measure that against a known standard. This is generally done by mass. The one that is generally used is KHP. We'll look at a sample of that in the problems that we do. But the moles of your standard, you take a mass of your standard, and using its molar mass, you determine the number of moles. That goes into your Erlenmeyer. It's dissolved in water, and then you titrate it with the solution from your burette. So the moles of your standard are titrated by the solution in your burette, and from the volume used out of your burette, you can calculate the molarity. It always goes back to the same equation we used before. Volume times molarity equals moles. So if you know the number of moles and you know the volume added, you can calculate the molarity. So those are the two types of titrations that you can be presented with. A gravimetric analysis, you've done one of these. You actually did the hydration. You calculated the number of waters of hydration in a hydrate. You take the mass of the solid at the start and you subtract the mass of the dry solid to determine the amount of water that was released. Using the molar mass of water, that allows you to calculate the number of moles of water. Using the mass of the dry solid, you can calculate the number of moles of your compound, and comparing those two allow you to calculate the ratio between the empirical formula of your dry solid and the number of moles of water. You did that in the lab that I'm grading now, which is lab number 8. You can also use that to measure ion concentration. If you have an ion of interest that's in solution and you want to precipitate it out of solution, you collect the precipitate and measure the mass. Calculating from the molar mass of that precipitate, you can calculate the moles of precipitate, and then you can calculate the number of moles of that ion of interest based on the stoichiometry in the compound, and work your way back to the molarity of that ion in solution. And we'll do a sample of one of those as well. The final, we've done this before, so we won't go through this very exhaustively, but we've talked about this before. This is an elemental analysis by combustion, where you have oxygen being taken into a combustion chamber. Your sample is in here. It's converted to carbon dioxide and water. And you have a chamber that first has a water absorber, such as magnesium perchlorate will absorb water. You can measure the mass of that magnesium perchlorate when it's dry before the reaction occurs. And then you measure the mass afterwards, and the increase in mass is due to water. From the mass of that water, you can get moles. From the moles of water, you can get moles of hydrogen. And so that allows you to calculate the mass of hydrogen in your original compound. The second chamber has a carbon dioxide absorber, such as sodium hydroxide. Again, you measure the mass of the sodium hydroxide before, the mass after. That allows you to calculate the mass of carbon dioxide. From that, you get the moles of carbon dioxide and the moles of carbon, which gives you the mass of the carbon in your original mass of your sample. Anything different, if the addition of these two is less than the original mass of your sample, then the rest must be oxygen, and you can determine the mass of the oxygen in your sample. From the mass of each of these, you can get moles, and from that, the empirical formula and the percent composition. So we've done that kind of thing before. So today what I want to do is I want to go through a couple of problems with you to show you how you might see some of these. And I'm going to share my screen for a moment to show you. We're going to actually do, I think, both of these problems today. So let me switch to my other camera. Okay, so the first one was a titration. And we have, before I actually do this problem, I would like to say that let's take a look at this. And we said that acids and bases actually break up in solution. So what we really should have here is an ionic equation. So we might want to have H plus aqueous plus Cl minus aqueous plus sodium aqueous plus OH minus aqueous. This is our full ionic equation. And on the other side, we still have sodium ion aqueous and chloride ion aqueous. But we have water as the other product as a liquid. Okay. If I can actually probably bring that down just a little bit. Okay. If I do the net ionic equation here, I notice that sodium ion and chloride ion are the same on both sides. So my net ionic equation is H plus OH minus forming water. That net ionic equation is exactly the same, regardless of what strong acid you use. This was HCl. Remember, we have 6 strong acids: nitric acid, perchloric acid, sulfuric acid, etc. It doesn't matter what the strong acid is, the net ionic reaction for any strong acid-base reaction is exactly the same because the counter ions will cancel on both sides. The difference is if it's a weak acid. If it's a weak acid, you cannot break the weak acid up into ions like this. So you're going to end up having to write the molecule there. So be aware of that. Okay, so because these are 1-to-1, hydrochloric acid produces 1 proton, sodium hydroxide produces 1 hydroxide ion. We can use the same equation we did before, which is V1 M1 equals V2 M2 is the generalized equation, which I might, in this case, rewrite as the volume of the acid times the molarity of the acid equals the volume of the base times the molarity of the base. The only time you would have to take into consideration, and we'll do this in the second problem, is if there's if this were, for example, magnesium hydroxide. Magnesium hydroxide contains 2 hydroxides, so the ratio of these 2 species would be 1-to-2, and so you'd have to take that into consideration in your stoichiometry. But remember that volume times molarity equals moles. So this is moles of 1 equals moles of 2. In my converted reaction, it means moles of acid equals moles of base, which is exactly what a titration is. So the endpoint was reached. In this case, let's see, we have, so we're gonna solve this. What we're trying to calculate is the molarity of the acid. The molarity of the acid equals volume of the base times molarity of the base divided by volume of the acid, if I rearrange this equation. So the volume of my base is 35.23 milliliters times the molarity of the base was 0.250 molar, and the volume of my acid was 50 milliliters. Notice that milliliters cancels, and I end up in the units of molarity, which is what I want. And it's 0.176 molar. 3 sig figs, because I have 3 sig figs here. These two were 4 sig figs, but this limits me. So it's 0.176 molar is my answer. Any questions on this one?
Professor,
Yes.
do you always have to show the net and ionic equations?
No, unless you're asked for it.
Okay.
I did this today because I wanted to point out to you that the net ionic equation for any strong acid, strong base reaction is H plus OH minus yields water. That I just wanted to point that out to you.
Professor, how will we know if it's a weak acid that won't do that?
You have to memorize the 6 strong ones.
Okay.
There's very few things that I want you to memorize in chemistry. For the most part, I want you to be able to think your way through problems. So I emphasize explanations and understanding as opposed to memorizing. But there are a few things that you will have to memorize. And the few things that you will have to memorize is the 6 strong acids. They are all the hydrohalic acids except for HF. So HCl, HBr, HI are all strong acids. HNO3 is a strong acid. H2SO4 is a strong acid. We're going to do some work with H2SO4 in second semester and qualify that slightly, but for now, think of it as a strong acid. And HClO4. So the hydrohalics, except for HF, nitric acid, sulfuric acid, and perchloric acid, those are your 6 strong acids, and all of them have this same net ionic equation. Weak acids are a little bit different. We will focus more on weak acids in the spring semester when we talk more about acid-base reactions. We're going to do a lot more on acid-base later, and we'll focus on those in the spring semester. Any other questions?
That last strong acid, that's perchloric acid, right?
Yes.
Okay.
Yes. Note that the others, chloric acid, chlorous acid, and hypochlorous acid, those are all weak. It's just this one. And we're going to discuss why. I mean, we're going to go into much more detail about acids in the spring, and we'll discuss why they're weak, why some are weak and some are strong, etc. Okay, so now let's look at the second problem that I wanted to do with you is on that slide was this one. A 20 milliliter sample of aqueous oxalic acid, H2C2O4, was titrated with 0.09113 molar solution of potassium permanganate, KMnO4. A volume of 23.24 milliliters was required to reach the endpoint. What is the molarity of the oxalic acid? Now, this one is not one-to-one. My balanced equation, and for those of you who are looking at this and saying, oh my gosh, how do you balance something like that? This was balanced using the method in this PowerPoint that we did not cover. It was optional. This is an oxidation reduction reaction that occurs in acidic solution. So before we do it, let's take a look and see if we can see what the oxidation reduction reaction is. If we look at manganese here in MnO4-, this is the anion from potassium permanganate. The oxygens are -2. Whole species has a minus charge. So your manganese here is a +7 oxidation state. This is a little bit in the shadow there. So it is a +7. If we look on this side, it is a +2. So our permanganate here has gained 5 electrons because it's gone from +7 to +2. If we went through the exercise and looked at the oxygens and the hydrogen, we would see that they did not change on this side at all. What does change is the carbon. Carbon here, if hydrogens are +1 and the oxygens are -2, then I have 2 carbons that have to total +6. My carbon is +3 on this side. On the other side, my carbon is +4. It's always good to check that. So my carbon going from this one to this one has lost 1 electron. Okay, so there's my oxidation reduction, and this is done in aqueous solution. It's done in acidic solution, and they're actually, I think they're kind of fun to balance, but that's because I'm a chemistry geek, I guess. Okay.
Why is it optional?
Why is it optional? It's optional for now. We're not going to make you learn how to do this at this point. Before we get to electrochemistry, you would have to learn how to do this. They're not, from my perspective, they're not hard, but they do take time to learn. And some of you may learn very quickly. Doing 1 or 2 of them, you'll get it right away and understand it right away. For some of you, it would take repetition, 3, 4, 5, 6 different problems before you finally figured out how to do this. And we just don't really focus on it now, but we will focus on it later. You will have to learn eventually. You just don't need to learn now. So in this case, we have to take into consideration the stoichiometry of this equation. So the first thing that I want to do is I have a molarity and a volume of the KMnO4, and this you have to tease out of the sentence. You've given the molarity of potassium permanganate. A volume of 23.24 milliliters was required, that is of this. So these are the 2 numbers. So I'm going to calculate how many moles of MnO4 equals 20. Now I can do this one of 2 ways. I can do this using converting these volumes into milliliters into liters, or I can do it leaving it as milliliters. It doesn't matter because I have both volumes as milliliters here. For the purposes of today, I'm going to convert that into liters. It really doesn't matter, but I have 0.02324 liters of MnO4 minus times the molarity, which is 0.09113 molar. That's going to give me 0.0021178, and I'm going to carry an extra significant digit because I want my answer in 4 significant digits. This is how many moles of MnO4 were added. I'm going to have to multiply that from the stoichiometry of the reaction. 2 MnO4 minus reacts with 5 oxalic acid. So 0.002117 moles of MnO4 minus times 5 moles of oxalic acid to 2 moles of MnO4 minus means that I have 0.005295 moles of H2C2O4, oxalic acid. That number of moles was contained in my 20 milliliter sample. So I can divide this by 0.0200